And hello, Rob Savard here, Air Assist Team. This video is to bring kind of everybody up to speed on where our build is. At this point, things have been moving fast, and I just wanted to recap everything we've been working on. First of all, thanks to everybody that's been helping out. Great group of people working on our open source ventilator, which means that once it's posted online, we will be able to tap the hive mentality, as Barry says, to continue to improve both safety features as well as capabilities of this unit that we have right now. So dangers and pitfalls. When we first started, we wanted to build a ventilator that protected against barotrauma and volutrauma. Too much air, too much volume that would hurt the fragile membranes of the lung. So that was our main design criteria to start with, even at the expense of the functionalities of the ventilator. We have to not hurt anybody. That's the whole goal. So ventilator overview. We right now have a fixed volume ventilator. So it is a fixed volume, otherwise known as a fixed tidal volume ventilator that also has, thanks to David Hempy, the ability to breath trigger as well. So let's talk about the build. Built around available components at an arm's length, both for the medical side, things that we find in an ambulance or the emergency room, and or things that we have at Home Depot, supply houses, and etc. Hobby-ish type of electronics too as well, built around the Arduino. The unit is also built to take advantage of hospital services such as hospital air, hospital vacuum, hospital oxygen, as well as hospital power. That means this thing does not actually have a power backup, assuming that hospitals all have generators. So we're not going to incorporate that complexity into the design because we did not feel it was necessary, at least not for this iteration. No fabricated parts whatsoever. No 3D printed parts, no laser printed parts. Everything, once assembled, should cost less than $300. We're about $280 right now, and built in several hours. A couple hours could put one of these together. A group of people can put several of them together in a day, which is what this is about, of course, obviously. So let's talk about our two distinct sides. All right, we designed this to have a medical side as well as an industrial side, and there is no connection between them, including the air that's delivered to the patient is separate. The only thing connecting the medical side with the industrial side is one pneumatic hose and one wire that goes to the pressure sensor in the inhalation tube on the patient's side. So we'll talk about the medical side. Bag valve mask. Air goes in the backside, as well as additional hospital oxygen going in the backside. They mix together before they're delivered to the patient. The bag valve mask has an emergency or a safety relief valve built in here, so protecting against overpressure, as we talked about. The mask comes off. It can either be used as a mask or with a endotracheal tube into the patient, and the bag valve mask is designed either in the ambulance or in the ER to accommodate either. I just have the mask with me today. David has everything else down in Lexington on the dummy with the endotracheal tube. The beauty about these is that one of the important things about ventilating a COVID patient is PEEP, which is basically a back pressure, maintains pressure on the patient above ambient even after exhalation, and that is to keep the lungs open. These are adjustable, and there's no sense in reinventing the wheel. They all come with the bag valve mask. Proven design, proven to be functional for ventilating in the medical system, currently being used, and that's what we're tapping to for our ventilator. We wrap a very common blood pressure cuff around the bag, and that's what provides our mechanical force for ventilation. This is controlled by the Arduino and the industrial side very carefully to provide measured ventilation to the patient. So medical side, let's move over to the industrial side. So what we have here is mostly a pneumatic system that is controlled by an Arduino programmable controller over on this side. We'll talk about the programmable controller first. Arduino, very common hobbyist type, but very stout and programmable device. They very simple to program. The code for this is available on GitHub, so if anyone wants to participate in improving the code, they can do so. A couple hours on YouTube, and you're setting up and installing the code on the Arduino. We have a relay board which controls our pneumatic valves, we'll talk about in a second, and we have a digital readout as well. So while we're here, we're going to talk about the digital readout. So the digital readout is shown in breaths per minute as well as inspiration-expiration ratio. And those are the two, those parameters are what the hospital folks speak of, and that's how they codify ventilation. So these are direct inputs into the Arduino. So we have rate and ratio here, and this requires two hands to actually adjust it. You have to press the ratio and then the up or down button, and then you can press the rate or the up or down button. By using two hands, that means that inadvertent changes of the baselines are at least reduced anyway by having to use both hands. We can see here we have 4 breaths per minute and 1 to 2.5 inspiration to expiration ratio. We also have coded in here inspiration and expiration, which shows the status of the Arduino and what it's actually commanding the system to do at this time. So there's the brains of the operation right now. I've incorporated a on-off switch just for the 12 volts on the relay, which is why the Arduino is currently running, and the valves are not actually working at this point. So I'm going to go ahead and turn the valves back. Well, I'll tell you, before we go into that, pneumatic side, we have a air regulator. We have 2 5-way pneumatic valves, 1 simple 2-way pneumatic valves, and some cylinders, air cylinders, typical air cylinders. The amount of air cylinders, the number of air cylinders does not matter. 1 big one, 2 medium-sized one, 3 small ones. They're all connected in parallel. It makes the design very adaptable to whatever you might have on hand. If you don't have a large, expensive cylinder, you can use 2 smaller ones. These were kind of about, I don't know, $12 each. If you happen to have a couple, 3 small ones lying around, that's even better. And we have needle valves, 1, 2, and 3. These are actually all the same valve. They just look a little different types. Any needle valve will do for the occasion. So I'm going to go ahead and turn on the system. There we go. And we can see that the Arduino is commanding the valves and the air coming in, and it's compressing our bag valve mask to push air into the patient on a controlled time frame. So the important part about Volutron is we don't want to have air being able to go directly from the regulator to the cuff, over squeezing the valve, pushing too much air into it. So there's no way for the air to get to the cuff directly from the regulator. The air must first go through, we call the tidal volume solenoid, goes to the back side of the cylinders and charges them, what we call a tidal volume pre-charge. The volume is fixed, the pressure can be changed with the air regulator. So obviously a little more pressure in the cylinder, a little more compression of the cuff. And that's how we adjust how much tidal volume is going into the patient. Once it's set, it's a very predictable compression on the cuff, predictable tidal volume going into the patient. It's resilient to multiple failures. You can have failures of both pneumatic valves and even a failure of the Arduino. Once this tidal volume charge has been expended into the cuff, there is no more air that can be directed into the cuff. I'll show you guys that. I'm going to turn this off for a second. I'm going to dry fire this mechanically, and you will see that it compresses. Once those cylinders are empty, there is no more air. Even though those valves are held open, I'm still holding those valves open right now. That's it. The cylinder has depleted, and all the air that's going to go into the cuff has gone into the cuff, and that's it. For there to be any more air to get to the cuff, it has to recycle one more time, recharge, and then it's ready for its next cycle, and we redo the cuff. So resilient to multiple failures, and seems like a very good way to control both tidal volume in a very predictable way, as well as increase the safety level of Volutron to the patient. So I'll go ahead and turn the valves back on here, and we'll start operating normally. All right. One thing we didn't cover as far as the Arduino goes is we do have in the the feed line to the patient is we have a pressure sensor in there, and Dave has coded in the ability to sense a drop in pressure when a patient takes a breath. When he aspirates, the pressure drops. The pressure sensor picks it up. The Arduino coding goes ahead and triggers a breath at that moment. So when the patient tries to aspirate, it delivers an immediate breath to the patient. So it's basically patient triggered, so it delivers it on command, if you wish. If there is no drop in pressure sensed from the patient, the Arduino will fire the normal cycle on its own, giving a breath to the patient no matter what. So, and last but not least, it's not on this board right now, but we have a battery-powered alarm system. The Arduino monitors through the same pressure sensor, overpressure. It also monitors for pressure cycles and power loss. If any of those conditions are met, it triggers the alarm. The alarm is battery powered, so even a complete loss of power to the system, the alarm doesn't rely on external power, so it will go off. If everything fails on it, the alarm sounds. The beauty of it is that you can come back here as a redundant mode. Given that the time that we developed this, we got to consider redundancy. The attendant or the physician can come along if this ever fails, and immediately begin manual ventilation of the patient, just with with what's currently set up through the endotracheal tube. So no additional steps whatsoever. They can bring over another ventilator or figure out what the next step is with the patient, or plug the system back in or whatever might have failed at the time. So we do have redundancy in case of failure, reverting back to a manual mode of ventilation right off the current existing system. All right, I need to show you guys how this is adjusted with the cuff compression speed. I'm going to turn this back on. So the idea is that the whole tidal volume pressure is delivered into the cuff during the normally on inspiration cycle. So I'm going to turn this off a little bit, and you'll see that with it closed down a little bit more, that the entire tidal volume is not getting depleted into the cuff during its normal on time. So I'm going to have to open it up a little bit because we want the full tidal volume into the cuff. And we just want it to basically bottom right at the end of the cycle, which is doing great right now, just basically bouncing off the end. I can go too far the other way, where it actually depletes before the end of the cycle. It's shooting all the air into the cuff, and then there's some cycle left, and it's all the air is gone. So it's very predictable with the needle valves. It's very, very controllable, very predictable. Once the parameters are set on the Arduino, or if any parameters are changed, a little tweak here just to make sure that the air is being pushed into the cuff over the whole duration of the inspiration time. You can see it's hitting bottom just a little early, so I'm going to kind of maybe tweak it off a little bit more, and you can see we just got both cylinders kind of bouncing a little early yet. There we go. Nice and predictable. They're bouncing off the cylinders. So the tidal volume is, and that's important too, because if you deplete all at once, you're actually increasing the pressure on the patient at the beginning of the breath cycle, and there's nothing left at the end of the breath cycle. So this has to be delivered over a smooth course over the whole inspiration cycle. Very important to make that happen, and we've accomplished that here. So the last thing we're going to talk about is the vacuum solenoid. The vacuum solenoid over here at the back, of course, is used to aspirate the air coming out of the patient. The air coming out of the patient is, it's water droplets full of COVID. You can't have that coming back into the room with the the workers or the other patients or even the patient himself. So. This will aspirate that air and send it over into the hospital air, which is what we've plumbed it to as well. The vacuum, another needle valve here, controls the vacuum flow so that we don't have too much vacuum accumulating behind the PEEP valve and possibly affecting its operation. So we have that there as well. We also have a check valve in the line as well in case there is a little too much vacuum that accumulates in the backside. We do have a check valve as a last resort to keep the vacuum from becoming too strong on the backside of the PEEP valve. And that's it, guys. Not a crazy sophisticated ventilator, compared to the big ones, but I think a darn good rendition for a $300 ventilator, thanks to David's coating with the breath triggering, and a good base design that I think that we can expand capabilities upon. We can expand some safety items on there too, as well as some capabilities. And hope that by putting this out there, we'll have a lot more contributors to the project, and have something really nice on our hands to help with this current crisis that we have. And thank you very much.